yeah, so the idea is to tell you about a few things about total positivity. And please feel free to interrupt and ask questions, of course, because this is full screen. I can't see any of you, but yeah, just ask questions. Also, this is, as Gaurav probably mentioned, I forget now, it's the first of 2 talks. Both are basically self-contained, but obviously there are lots and lots of connections between the two because they are both on total positivity. And finally, yes, I am writing a book, but it's about many things, one of which is total positivity. And so it has roughly 6 parts. And the yeah, this introduction part is part 4, where I develop all these things in sort of as much detail as I can. And it's a beautiful and fascinating subject. What is remarkable is using very little, people have proved very much. So Polya and Schur proved this thing about multiplier sequences, which led Schoenberg to total positivity and Polya frequency functions. Also, Fekete and Polya built on some work by Laguerre, or Fekete did, and then Polya built on some more work. And there's lots of fascinating history. And in my book, in my notes, which are on my webpage, they're lecture notes. I have tried to explain these results, the progression of ideas, and the history as well. So in some sense, total positivity, or one of the important characterizations of that, called the variation diminishing property, goes back to the 1600s. And that will be discussed in my next talk. Okay. So let me begin. So let me start with something that's maybe far a little simpler, positive semi-definiteness or positive definiteness. So a real symmetric matrix is positive definite if there are these 3 conditions, they are equivalent. So one is the name comes from the quadratic form being positive definite. If and only if all the principal minors are positive. So you take a set of rows and the same set of columns, the same indexed set of columns. That submatrix is a principal submatrix and its determinant is positive if and only if all the eigenvalues are positive. Right? So this is very standard. It's a folklore result. It shows up in many places in analysis and, of course, in the applied sciences via correlation and covariance matrices and so on. Of course, it shows up in the second derivative test as well. Right? So a long time ago. In parallel, then, a real but not symmetric, a rectangular matrix, in fact, it need not even be square. So a real rectangular matrix is totally positive if all the minors, so you take any set of rows and the same number of columns, but not the same set of columns, that determinant has to be positive. And if instead all the minors are non-negative, then this is totally non-negative. So for example, all the entries are positive for a totally positive matrix, all the 2 by 2 minors and so on. Right? And these matrices occur in a lot of different areas in mathematics. I will in fact give you, so in my next talk, I have a whole slide with all these areas and names of some of the people who have contributed to them, from all the way from the early 1900s to the late 2010s. So it has been going on for a long time. So let me give you some basic properties of totally positive matrices. So the idea is that these are similar, quite analogous and similar to positive semi-definite matrices and their properties. So first of all, spectral properties. So suppose A is a real symmetric matrix, then as I just told you, these 2 properties are equivalent. All the principal minors are positive. That's the definition, if you will, if and only if all the eigenvalues are positive. So clearly 2 implies 1, right? Because every minor is but then for that I need to take the eigenvalues of the principal submatrices as well, right? Not just the eigenvalues of A, but implies 2 is trickier, but that's exactly Sylvester's criterion. This is again a folklore result. In parallel, this is a well-known result of Guntmacher and Krein. So now let's take a square matrix for discussion's sake. All the square submatrices of A have positive determinant. That's the definition, again, of total positivity. If and only if all eigenvalues of, again, I take all square submatrices, no longer just principal, but all square submatrices, all of those have positive determinant, eigenvalues, right? And I'm actually going to prove this for you in the next slide, or give you a sketch of that. And the proof uses 2 very classical results. One is Perron's theorem, so the precursor to Perron-Frobenius. So this is Perron's theorem for matrices with all entries positive. And the second is Kronecker's theorem, which is even older, I guess. Perron's theorem is 1907. I believe Kronecker is older. So what is the reason? Again, of course, 2 implies 1 is obvious. If you have positive eigenvalues for a given square submatrix, the determinant is positive. What about the converse? So let me start off with Kronecker's theorem. So it starts with the compound matrix. So given a matrix A, let's say a square matrix A, you look at, so for the R by the R's compound matrix, you choose any set of R rows and any set of R columns. So there are n choose R choices for each of them. And so I have an n choose R cross n choose R matrix whose jkth entry is precisely the determinant of the submatrix. And I lexicographically order the sets. So fine. So for some basic properties, by convention for R equals 0, this is not a true definition. So we set the definition to be the 1 by 1 matrix 1. For R equals n, I again get the 1 by 1 matrix whose entry is the determinant. So that's this matrix here. The R equals 1 case, I take all the 1 by 1 minors, meaning the entries, and I just get A. So these are just some obvious properties. What is slightly less obvious, but you can prove using critically that it's lexicographically ordered, is that if A is upper or lower triangular, then the compound matrices are also upper or lower triangular. So if you intersect these 2 properties, if A is diagonal, then the compound matrix is diagonal. Not only that, suppose A is diagonal, what are the entries on the diagonal of the compound matrix? Well, the diagonal entries would be the j comma j entry, and that would be the determinant of the principal submatrix, which means you just take R-fold products of the eigenvalues of A. Right? Those are the diagonal entries of A. In fact, that goes through for for triangular matrices as well. The eigenvalues lie on the diagonal. So if you take the triangular compound matrix, it turns out that the diagonal entries are precisely R-fold products of the eigenvalues. So that is a useful thing to keep in mind for just now, for presently. Also, you have symmetric matrices. It preserves the same properties. That's fine. Cauchy-Binet formula. If you look at if you unpack the formula itself, you literally get this definition, this property here. Okay, so this property also therefore implies that if you take the inverse of the compound matrix, that's the compound matrix of the inverse, because CR of identity is the identity, and you can check. So now with this, with these preliminaries on compound matrices, let's prove the spectral property for totally positive matrices. First statement. So let's write down A in Jordan canonical form. So A is something like this. J therefore is triangular. Now I take the compound matrix on both sides using the Cauchy-Binet, and I get exactly this identity. And the middle matrix is again triangular. And so it contains the eigenvalues on the diagonal. But what are the eigenvalues of a triangular matrix? These are R-fold products of the eigenvalues of J, meaning of A. So I know that the diagonal entries here are the R-fold products of eigenvalues of A. Right? And so until now, I have only been using Kronecker's theorem. Now here is where Perron steps in. So let's number the eigenvalues of A in decreasing order of modulus. These are, of course, all complex numbers. So if A is totally positive, remember that this matrix has all R by R minors of A. So because it's totally positive, all of these entries are positive. So this matrix itself, the compound matrix, has positive entries. So Perron's theorem says it has a Perron eigenvalue, which means it's a simple and positive eigenvalue. But we know all the eigenvalues of this compound matrix. These are precisely R-fold products. Therefore, this Perron eigenvalue must be the product lambda 1 times lambda R, and this is real and positive. And now I think we are so that basically means we are done, because what I know is lambda 1 is positive, lambda 1 times lambda 2 is positive, so lambda 2 is positive, lambda 1, lambda 2, lambda 3 is positive, and so on. And so every lambda j is positive. But moreover, I know that the Perron eigenvalue is simple, which means lambda 1, lambda 2 is bigger in modulus, or well, these are all positives. It's bigger than lambda 1, lambda 3. So lambda 2 is bigger than lambda 3. And then lambda 1, lambda 2, lambda I is bigger than the I plus 1 product. Sorry, so then lambda 1, lambda 2, lambda I minus 1 times lambda I plus 1. And so you get that all of these values are strictly decreasing. And I believe that is the original proof by Guntmacher and Krein in 1937. So yeah, this is why totally positive matrices have similar spectral properties to positive semi-definite or positive definite matrices. And this is for totally positive, but then you can, of course, take limits by the continuity of roots. For continuity of polynomials and roots, you get that the totally non-negative matrices have non-negative eigenvalues. These may not be simple. For example, the 0 matrix has all eigenvalues 0. Okay, so yeah, if there are any questions, again, please feel free to ask. Okay, now for some examples. So, of course, so this is a non-trivial example. Well, non-trivial, but it involves an explicit calculation. Let me say that. Take a square matrix with zeros below the diagonal, ones on and above the diagonal. That is totally non-negative. Of course, there are 0 minors because there are 0 submatrices.
Actually, Apoorva, there was a question.
Yes.
So I just missed the theorem. What the statement of the theorem was that you proved?
The theorem was that if all minors of a matrix are positive, 1 by 1, 2 by 2, everything, then all the eigenvalues of every square submatrix are positive.
Okay. And you were doing all this for the eigenvalues of A n cross n, I thought. So,
yes. But the point is, if you take any square submatrix, then it has the same property as 1, and therefore its eigenvalues are positive.
Oh, right.
A minor of a submatrix or a submatrix is a matrix.
Okay, so, yeah. I get it.
Yeah. Okay, great, thanks. So so now going back, so this is one example. The prototypical example, of course, is this second one, the generalized van der Waals matrix. So you take positive bases in increasing order, real exponents in increasing order, then the determinant is positive. And this uses Descartes' rule of signs, which, as I sort of hinted at, is the moral progenitor, if you will, of the variation diminishing property. But I will get to that and the proof that this determinant is positive in my next talk. Again, it fits on one slide and it's very easy. But this thing of why Descartes and from Descartes to Fekete and Polya, that historical journey is, I'm keeping it for my next talk. Using this generalized van der Waals, I can prove a third kernel, a symmetric one, is totally positive. And that's, I believe, an observation of Polya, but that says that the Gaussian kernel is totally positive. So, of course, all of us know the Gaussian density. So, given any increasing tuples of real numbers, xj and yk, if you look at e to the minus, so I choose some variance parameter and then look at this variance or inverse variance. This matrix is totally positive. Okay. Why? Because the matrix itself can be factorized as a product of three things, of three matrices, and here they are. So, by the way, again, for the same reason as the question just asked, a submatrix of this looks exactly like the same thing. So, it's enough to show that the determinant is positive for this one matrix, hence for all submatrices. But this matrix itself factorizes, as I just mentioned here. This xj square term on the left, the yk square term on the right, and the cross term in the middle. Well, the first is a diagonal matrix, the third is a diagonal, so those determinants are positive. And the matrix in the middle is precisely a generalized van der Waals matrix. The xj is replaced by this thing here, e raised to 2 sigma xj. So I crucially need that the minus sign here cancels with the minus sign here. That's why I get a plus here. And so this is increasing, the yks are increasing, and I'm done. So a kernel is just a function on x cross y for two sets x and y. Of course, in this case, because I want total positivity, I want the domains to be ordered. So I need to take a function based on two linearly ordered or totally ordered sets, x and y. And then all I'm saying is that I draw so many entries from x, the same number of entries from y, pick up a submatrix, I draw a submatrix, the determinant is positive. Yeah, that's all that this is saying. Okay, so I'll get to kernels in a couple of slides, but first let me tell you another property that is similar to positive semi-definiteness, density. So recall that every positive semi-definite matrix can be approximated by positive definite matrices, right? Just add perturb by a small multiple of the identity, take epsilon to 0 plus. So the eigenvalues all increase by epsilon and epsilon goes to 0. So the non-negative so the positive eigenvalues go back to the non-negative. Okay, so density also holds for totally positive matrices inside totally non-negative matrices. So this is a result by Anne Whitney. What she proved was, so Whitney was a student of Schoenberg, it seems. So what Whitney proved was the following. So I need to maybe define this TPR. So TPR means totally positive of order R, meaning the 1 by 1 minors, the entries are positive, the 2 by 2 minors are positive, all the way until the R by R minors are positive. But the larger minors can be negative. So, and there do exist examples like this. Okay. So the set of M by N, so take any rectangular matrices, fix a size, fix an order of total positivity, then the totally positive matrices of that order of that size are dense in the totally non-negative matrices. And the proof is not too hard, and the proof actually uses the lemma of Polya on the Gaussian density that I just told you, the total positivity of the Gaussian. Anyway, the proof is not too hard, but I'll skip it. So the same proof that can be written down, that Whitney wrote down, in fact, goes through verbatim for symmetric matrices. And it also goes through for continuous versions, that is kernels, which is where I come to now. Well, for certain versions of them at least. So here we go. Given two totally ordered sets and a map or a kernel, we say that the kernel is totally positive of order R. If given any size less equals R, the submatrices, all possible submatrices are positive, have positive determinant. So this is just the infinite analog of a matrix. If X and Y were finite sets, then you would get matrices of that dimension. This is now a function. And then again, we say K is totally positive if it is TPR for all R. And if you replace the strictly bigger than 0 sign, the strict inequality here by non-strict, you get Tn and Tn. So examples, X and Y finite give you matrices. Example 2 is a symmetric kernel on R by R. So take any sets of real numbers, finitely many x1 through xp and y1 through yp. If you look at this matrix, then this is totally positive, or the determinant is positive. Why? Because it's just a generalized van der Waals determinant. Right? It's just e raised to xj overall raised to yk. So that's again just a determinant. Now the next example follows directly from that. If you look at k plus minus of xy, which is these, so I put plus minus and the same plus minus here. These kernels are totally positive. The minus I explained to you because the cross term becomes plus. Well, for the same reason, if I take plus and plus, the cross term is still a plus. So this matrix would also factorize, and I get total positivity. And the determinant is positive. So if you take minuses, those are functions that depend on x and y only through x minus y. And there is a name for such classes of functions or matrices. These are called Topless matrices or Topless kernels. If you take plus and plus, then those are called Hankel kernels. And so let me start with Hankel kernels. So this I just told you is an example of a continuous Hankel totally positive kernel. And Hankel just means there exists some function of x plus y so that this kernel equals that. Right? It turns out that Hankel totally non-negative kernels and totally positive kernels can be characterized and have been characterized in a very classical result of Widder in the bulletin of the AMS. So suppose x is an open interval and you look at continuous Hankel kernels, which are totally non-negative. They have to be of this form. So it's some kind of a Laplace transform kind of thing. And of course, needless to say, this is written, this shows up in his book on the Laplace transform as well, and Widder's book. So basically, you integrate against some non-decreasing function, against some non-negative measure, the function x of minus x plus y times u. Okay? And this kernel is totally positive if and only if this measure has infinite support. Otherwise, it has finite rank, the rank being the size of the support. So if it's just a finite atomic measure, then the rank is finite. If not, then it's infinite. Okay. And for such kernels, as I said, Whitney density, the density theorem held for matrices, well, it certainly holds for Hankel kernels as well, because you can just perturb by a small multiple of a totally positive Hankel kernel. So as epsilon goes, so this has infinite support on 0, 1, and so this thing itself is totally non-negative, and you can check that the sum of two, well, actually, you don't need to. You use Widder's theorem to say that the whole thing is of the same form with infinite support. Right? And as epsilon goes to 0, this goes to any totally non-negative. Okay, so this is Widder's theorem and the corresponding density for Hankel kernels. So now let me go on to Topless kernels. And those have that's where I'll sort of spend the rest of this talk, in the land of Topless kernels. So the Gaussian kernel, as we saw, is totally positive from above. And more generally, let me define a totally non-negative function. So now I look at one variable, not two. a function from R to R such that the corresponding Topless kernel is totally non-negative. So that's what we call totally non-negative functions, or TN functions. And I'll give you some very important, sort of almost the functions to look at. Here is one, e to the minus x squared. That's exactly the reason is because this is T lambda. This is the kernel. And that's not just totally non-negative, it's totally positive. Another example, I look at the Dirac functions. So I fix one point and I take one non-negative real number, and that's the mass at that one point. And the proof is written in the parentheses, right? Draw some submatrix if, so you have some lambda of xj minus yk. So if some xj and yj differ, something. So if all the xj's are different from, if some xj and yj differ, then you get a row of zeros or a column of zeros in the matrix. So the determinant is 0. If all the xj's equal the yk's or the yj's, then you get a diagonal matrix, and that of course is non-negative determinant. So this is easy. But this is sort of a pathological example. It's non-zero only at one point. This is nice. It is positive everywhere. Okay. The next example is also positive everywhere, but it is very different because the previous two were non-monotone, and this one is monotone. Right? So of course, you can take a constant when a equals 0, or you can take a to be non-zero, in which case it's strictly increasing or strictly decreasing. In that case, I claim that this kernel is totally non-negative. Why? Because if you take this submatrix, then this is literally a rank 1 matrix. Right? It's just the column vector e raised to axj's times the row vector e raised to minus ayk minus b. So all 2 by 2 and higher minors vanish. The 1 by 1 minors are the entries, and the entries are positive. So this is Tn. And there is a fourth example, and that is an example which vanishes. You see, this example vanished nowhere. This vanished on both sides of the origin, or one point. This example vanishes on one side. Right? So it's the Heaviside function, where you vanish on one side of the function. Okay, so this can be verified again by explicit calculation. In fact, if you remember the first example of a Tn matrix that I told you, zeros below the diagonal, ones on the diagonal, and ones above the diagonal, that exactly corresponds to drawing the submatrix from this and maybe taking the transpose. So all the minors are non-negative of that matrix and hence of this kernel. And check that the last two examples are not integrable. Okay, and now, however, you see, you can multiply by an exponential factor here to make it integrable. And that will be important in a second. That's one of the foundational results by Schoenberg. So without further ado, let us get on to Polya frequency functions. These are functions which are integrable. So they are totally non-negative. This kernel is Tn. They are also non-zero at 2 points. So they are not pathological, and they are integrable. So let's go back to the previous examples. So this function is satisfying all the 3 properties. It's Tn, it's not pathological, and it's integrable. That works. This is pathological, so not a Polya frequency function. This is not integrable. It is certainly Tn and non-zero, but not integrable. So that's the property that fails. Right? So this is one property fails here, it's pathological. One property fails here, it's integrable. And here it is non-zero and Tn. It is not integrable though, yeah. But let's see, non-zero 2 points. Yeah, okay, so what do you do here? Well, here you can make it integrable, as I said, by multiplying by an exponential factor. And that turns out to happen for all totally non-negative functions. You have a trichotomy. Either the function is pathological, or it's an exponential, or you can multiply by an exponential factor and make it a Polya frequency function. So I don't know if I'll say that, but let's see. So yeah, so let's move on to examples of these functions and mention. Okay, before that, let me mention that they connect to a lot of different things. I'll mention some of the connections in this talk and at least one connection by Karl-Heinz Groschning in the next talk from last month, actually. Which, yeah, the connection, as he himself remarks, should probably have been made in 1951, but apparently in 70 years, nobody made it. So he makes that connection in 2020. So examples, the Gaussian kernel, yes. This one, as I just said, you can multiply by an exponential. Okay, why is this Polya frequency? Because, well, it certainly is integrable and non-zero at 2 points. Why does it stay totally non-negative? That's because of the same kind of Gaussian trick, right? You take some submatrix and you check that it factorizes into 2 diagonal matrices. and the middle matrix. So T lambda, this T lambda is totally non-negative if and only if T delta is totally non-negative. So multiplying by an exponential factor does not change the total non-negativity. So how does one construct more examples? So one way is to take convolution. So some ways I told you, I mean, multiply by some of the exponential factors. As long as they stay integrable, you still get Polya frequency functions. Another way is to take convolution. So before I tell you about convolution for the functions, let me tell you about the discrete case. In the discrete case, convolution just means usual matrix multiplication. So given two matrices which are both Tn or Tn of some finite order, why is the product also totally non-negative of that order? And that's precisely the Cauchy-Binet formula, right? So given I and j's, rows and columns of size less equals r, you can compute the I by j minor of a product in terms of the I minors of the first factor and the j column minors of the second factor. And now if by assumption this determinant is non-negative and this is non-negative, then the sum is non-negative, and you're done. So this is just a simple application of Cauchy-Binet. But now this formula also has a continuous version due to Polya and Zigo in their book on problems and theorems in analysis, 1925. So that version, I think Carlin calls it the basic composition formula. And as a corollary of that, here is its theorem. So if you take integrable totally non-negative functions, then their convolution is integrable and their convolution is totally non-negative. The second part follows from this continuous Cauchy-Binet. And that's going to give us additional examples. Okay, so, okay. So let's look at examples. So as I said above, this function is Polya frequency. Convolve and convolve and convolve again. So you get the repeated convolutions of these guys. They have to be Polya frequency functions as well. This actually, all of this, so the definition of Polya frequency function was in 1951 by Schoenberg, the full paper, and then there were some announcements in PNAS in 1947 and 48. So he provides this example in 1951, and he therefore convolves and says that these are examples in in the same paper. Then it's maybe a natural question to ask, what happens if this n here is fractional? If it is not a real power, but some kind of x to the pi times e power minus x. Is it Polya frequency? The answer turns out to be no, it isn't. But it is Polya frequency of certain orders. So which order? So meaning that maybe not all the 1 by 1, 2 by 2, 3 by 3, not all of those determinants are non-negative, but all the determinants until a certain order are non-negative. And this was observed by Sam Carlin, hence the slide and the title of the slide. So it turns out that non-integer powers are never Tn, in fact, but they are Tnr for various r. And so here is the theorem of Carlin from in the transactions. So let r bigger equals 2 be an integer, and look at alpha, a power which is either a non-negative integer or bigger equals r minus 2. So integer, 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 and then every real power above r minus 2. X to the alpha multiplied by that function above is Tn of order r. So that's what Carlin proved. The question, of course, was what about the remaining powers? What about the powers below? So it's easy to show that negative real numbers don't work. So what about the positive real numbers which are not integers and which are below r minus 2? What about those powers? Surprise! So this is mentioned in his paper. Carlin, of course, then wrote this famous book on total positivity, and it's mentioned in the book. And somehow I could not find what about the remaining powers having been addressed in the literature after that. So again, last month I was able to answer the question. The remaining powers are not Tnr, and this is just a weak version. The actual statement is that they are generically not Tnr, meaning you take generic x's and generic y's, draw the submatrix. That determinant is actually, well, that submatrix has a principal, has a minor which is negative, and in fact a principal minor which is negative. So generically, you draw any submatrix, it has some negative minors. It cannot have all positive determinants. Okay, so and the interesting thing about this set, so what therefore characterizes this kernel, if you will, is this kernel encodes this set of powers that are totally non-negative of order r. These powers occur in an entirely different setting of positive semi-definite matrices in 1977. So Loebner was apparently motivated by the Bieber-Bach conjecture and wanted to answer the following question in this connection. Take a positive semi-definite real matrix. So let's say a real symmetric matrix. All the entries are positive, and I raise every entry now, and let's say R by R matrix. So take the same R by R matrix, which is positive semi-definite with positive entries, and I raise every entry to some alpha power for the same fixed alpha. Which alpha preserve positivity? So actually, I work on positivity preservers, and so I knew this question at least 5 years ago, at least, for sure. I did not know this result of Carlin until 3 months ago, but this result I knew 5 years ago. And so the answer turns out to be every power. The answer turns out to be this set here. Yeah, so all non-negative integers preserve positivity, and all non-integer powers bigger than r minus 2 preserve positivity. The smaller powers here do not preserve positivity, and Fitzgerald and Horn proved that statement. Both of these. So some of these two problems have exactly the same set of answers. And it is the curious fact that I find fascinating is Loebner was a faculty in the math department at Stanford, and Fitzgerald and Carlin in the stat department. And this result, the one implication of this theorem of positivity was known to Roger Horn because of Loebner's observation in 1969. And it appears in Horn's transactions paper in 1969. Excuse me. But somehow, they were sitting next door, but somehow Horn never mentions this result of Carlin. And I recently asked Roger Horn after I found this converse, and he did not seem to know of this result. So it's very curious that these two occur in entirely different papers and sort of subdisciplines of positivity, but very close to each other. It turns out that there is further closeness. They both can be proved using the same technique. There's a common technique that ends up proving both of them, which was not available until 2020. And maybe this is why this converse result wasn't known. So this is a paper by Tanvi Jain of IISc Delhi. And it builds on the paper of hers with Bhatia, and then another paper of hers in 2017. But in 2020, she brought out a paper where she proved some results, and the same techniques can be used very, very nicely to prove this. It just works out beautifully to prove this result of this converse result of Carlin. So it's all thanks to Tanvi's paper, I would say, that this works. But anyway, so the answer is that there is some arithmetic progression, a finite arithmetic progression, and then a semi-infinite axis. For people who have seen who do complex analysis or representation theory, or probability theory, actually, this set or a very similar kind of set occurs in all of those settings as well, and that's called the Wallach set. So Nolan Wallach was studying something about principal series representations and so on, discrete series, and he classified. So he was trying to understand some unitarizability conditions. So on the side, Michel Verne and Rossi. So Rossi and Verne were understanding something about which powers of the Bergman kernel are reproducing, are reproducing kernels for some Hilbert spaces of holomorphic functions, and all of these things turn out to involve understanding which real parameters sort of satisfy some conditions. In all of these cases, those conditions are precisely an arithmetic progression and a semi-infinite set. And there is some connection probably, but I don't know anything beyond the superficial connection. So I'll maybe take the time right now to mention that, as Gaurav mentioned, I'm writing a book. It actually grew out of lecture notes on positivity preservers that I taught here at IISc. And it builds on old results of Schoenberg and Walter Rudin and other people. But I've just finished adding a bunch of this on Polya frequency functions and so on to the text. And the text is available online with a bunch of proofs, with sort of almost complete proofs if you can. And the technology, the prerequisites are quite low because amazingly, Polya and Schur and Schoenberg used very simple tools, but extremely clever and beautiful arguments to come up with all these powerful results. And so I've tried to capture some of that history in the notes. Okay, so now going back, but I digress. So coming back to Polya frequency functions. So as I just said, convolution gives you lots of examples. Oh, sorry, for completeness, let me finish the probability connection. Non-central Wishart and central Wishart distributions also depend on a shape parameter and some scale parameter or origin parameter. I forget, I'm not an expert, which also turns out to have to lie in some kind of set like this. That's called the Gindekin set in that connection. And there are some studies by Berezin in the quantum setting which also involve something like this. So this kind of a set shows up all over mathematics, and now it shows up in positivity and total positivity as well. Okay, so back to Polya frequency functions, then back to the main theme. As I said, if you convolve two Polya frequency functions, then you get one more as well. Right? There's another nice operation that behaves well with respect to convolution, and that is the Laplace transform. So let me now get to that. So first of all, two more examples, and then we'll get to Laplace transform and use these crucially. First of all, you can shift the origin, you can shift the scale, and you get a Polya frequency function again. Basically, the set of submatrices is the same. Up to maybe reversing the rows and reversing the columns simultaneously. But that's if you take A to be negative. Also, if you take a limit of a sequence of Polya frequency functions and the limit is integrable, then, and of course not pathological, then it also is a PF function. So that's just because you fix your arguments xj and yk, then lambda of xj comma minus yk is the limit of lambda n of those. So the determinant is a limit of determinants which are non-negative, and you're done. Okay, so these are just some easy, obvious examples of how to obvious recipes of getting more examples from old ones. Now for the Laplace transform, well, I guess we all know what it is, but here is the formal definition. Whenever this converges, because a Polya frequency function is integrable, this Laplace transform always converges on a strip in the complex plane containing the imaginary axis. Okay? So it converges around the imaginary axis, and fact, of course, you can verify is this is an algebra map. And so it's additive and it's multiplicative with respect to convolution. Okay, so now for more interesting Polya frequency functions. So I just told you on the last slide that this function e raised to minus x times the Heaviside function is a Polya frequency function. By rescaling, I get this function phi a is also Polya, and its Laplace transform is easily computed, 1 over 1 plus as. So this is one example of a PF function and its Laplace transform. Now let me convolve. So let me take a summable sequence of strictly positive real numbers. Let me take them to be strictly positive, all of them. Then for each n, I take the partial product, if you will, the partial convolution. And that is, again, a one-sided PF function. You can check it vanishes on minus infinity to 0. And its Laplace transform is the product, as we just said. It's multiplicative. Now you see that the claim is, first of all, that this function on the right-hand side, the sequence of functions, converges at every s. And that's just the usual stuff, right? Because since the aj's are strictly positive, if you take the absolute values on here, then you get 1 plus aj times mod s. And the product, that is less than e raised to aj times mod s. And now you can just take the summability here. So the product on the right-hand side converges, which means that the Laplace transforms, the sequence of Laplace transforms converges, and you can check it converges sort of, absolutely, and beyond some point it is integrable and nice things happen. So by the standard nice arguments, if you will, because the Laplace transforms converge nicely, therefore you can now apply the Mellin transform and go back to say that these partial convolutions converge nicely. And so before that, I need to do one last transform, but that's just simple. I shift the origin. So I make the origin in this way. Now, again, these things converge nicely, if you will. Therefore, the Mellin transforms converge nicely. And I get the limit of these Polya frequency functions. I get a Polya frequency function whose Laplace transform is e raised to minus delta s divided by the infinite product. If you take the reciprocal, guess what? You get an entire function. Right? And of course, delta is non-negative here, because I assumed that. And aj is strictly positive, let's say, or non-negative is fine as well, but eventually. These functions are actually very classical. They were studied more than 100 years ago by Laguerre in the 1880s and Polya in the 1910s, and people in between. So before I get to those functions, let me tell you why these functions are special. So on the one hand, these functions are special because of the title here, the Laguerre-Polya class. That's what they are. But remarkably, I told you that if I take some standard one-sided Polya frequency functions and I take the Laplace transform and limits, I get to a Polya frequency function of this form. it turns out every Polya frequency function is of this form. So theorem by Schoenberg, this is the first of his two theorems on these functions. A function which is which integrates to 1. So frequency functions in Schoenberg's time meant what we call probability density functions. The integral is 1, the functions are non-negative. Right? So this is a one-sided function vanishing on the negative side if and only if the reciprocal is a Laguerre-Polya class function. And the parameters are e raised to delta s and then 1 plus aj. So one observation, if I look at this function on the right, it's actually a limit of polynomials, and polynomials with strictly negative zeros. Here are the polynomials. So e raised to delta s is the limit of this factor here. The infinite product is the limit of this factor here, the partial product here. If of course some aj is 0, then that's 1, so I disregard the factor. If delta is 0, I disregard the factor because there is no factor itself. So the polynomial still has negative roots. Right? So that's exactly the defining property of this Laguerre-Polya class. So I'll mention that on the next slide. So this was the one-sided function. So every Polya frequency function vanishing on one side has to be of this form. Its Laplace transform is like this. It is a limit of functions which are convolutions of one-sided heavy-side functions. Similarly, you can look at the opposite, so the reflections of those heavy-side functions. So instead of saying e raised to minus x times 1 when x is bigger than 0, I can take e raised to plus x times 1 if x is less than 0, the reflections. I take those reflections, I take the original ones like these, and I take the Gaussian kernels. Again, using convolutions and limits of Laplace transforms and take the Mellin transform and so on, sorry, I get Schoenberg's other theorem. So we get one implication of Schoenberg's other theorem, which is that, yeah, if a function, again, which is a density function, is a Polya frequency function in general, if and only if its Laplace transform reciprocal is of this form, with the following suitable values of the parameters. And once again, by the same kind of trick, like this, you can find some polynomials with, this time just with real zeros. They don't need to be all positive or negative. For instance, I never mentioned that delta or aj are all positive or all negative. So the zeros of the polynomials approximating the reciprocal here are real. But yes, the reciprocal of that is a limit of real polynomials and real rooted polynomials. And these were very well studied by Laguerre, Polya, and Schur. The first class of entire functions, as I said, are limits. So you can take uniform limits on compact sets of polynomials with real non-positive roots. You can also, so this was the original result of Polya and Schur, Laguerre and Polya. But then Polya later on showed, and other people, Khorevar and Levin and so on, improved it to say, Polya, Lindwart and Polya later showed that you don't need to take uniform limits on every compact set. It's enough to take it on one. And then people reduced that one compact set from a disk to an arc and so on. And the second class, which is the class of functions here, are limits of real polynomials with real roots. They can be positive or negative. There are also limits of, the roots can also be at 0, and that is forbidden because of the reciprocal here, but the Laguerre-Polya class itself allows for an extra factor of, the value at 0 need not be 1, and the value at 0 can be 0. So these are, so we've gone back, so I'm sort of going back in time to some extremely classical objects in analysis. And this really stems, this understanding this class of functions that Laguerre was doing and Polya was working on, really starts from understanding roots of polynomials. Where in the complex plane do roots of polynomials lie? Now, do they lie in sectors? Do they lie on a line, in a strip, on a disk, and these kind of things? Okay, and so finally, let me bring you to the hypothesis that I mentioned in the abstract. The Laguerre-Polya class is distinguished for several reasons, and here is one of them. So in 1927, Polya initiated the study of functions whose Laplace transform is only real zeros, and his work contains this result, which I think is well known to experts, or to many people, more people, I guess, than just, so the Riemann psi function, which of course many of us know, is in the Laguerre-Polya class if and only if the Riemann hypothesis is true. And in fact, the real rootedness of this function was exactly how Riemann in fact framed his original hypothesis. So apparently the story goes, I read it somewhere, I forget, I read it in some paper or some historical paper, I forget where, that is why people were really trying to understand the Laguerre-Polya class and functions leading back to it, like the Polya-Schur multipliers, Schoenberg's theorems, and so on, because they felt that if one understands this sufficiently well, maybe just this was, of course, only talking about the real properties of it in some sense. But if one understands it sufficiently well, then one has the Riemann hypothesis. And I guess, unfortunately, 100 years down the line, we are still not done. But yeah. So that is just one fun connection, if you will, historical connection. Some more history then. The Laguerre-Polya class is related to these Polya-Schur multipliers, which bring us to more recent, let's say, gems of modern mathematics. So this is still very classical. So the multiplier sequence has the following property. So take a sequence of real numbers, and now it operates as a linear transformation of spaces of polynomials. So take a polynomial and consider the diagonal operator with respect to the standard monomial basis. So P naught becomes gamma naught P naught, P1 becomes gamma 1 P1, Pn becomes gamma n Pn. So just multiply the coefficients by these specific real numbers. For which real numbers, for which real sequences, do you start with a real, if you start with a real rooted polynomial, do you end up with a real rooted polynomial? If the polynomial starts by having real roots, it has to end up having real roots. Which sequences work? Okay. So this is a definition again by Polya and Schur. So gamma is a multiplier sequence of the first kind. If you start with a polynomial with real roots, you end up with one with real roots. And
gamma is an infinite set, right? Infinite sequence.
Is the entire set like this. So yeah, beyond this point, you would multiply by 0, 0, 0. I mean, the coefficients gamma, n plus 1, and so on don't matter because the Pn plus 1 and so on are 0. Right? So yeah, so gamma is a multiplier sequence. If for all polynomials of arbitrary degree, with all real but real rooted, the transformed polynomial under this diagonal operator has real roots as well. If instead you force it to preserve real rootedness on a smaller set of polynomials, meaning just the polynomials with negative real roots, then those are called multipliers of the second kind. So clearly, the first kind of operators are a smaller set because they have more constraints. They have to look at polynomials with all kinds of roots. And the second kind of operators are a larger set. And now the famous result, a sequence is a multiplier sequence of the first or second kind, if and only if the generating function is a Laguerre-Polya function of the first or second kind. So this is a famous result, again, more than 100 years back. Remarkably, so if you take as a black box the Laguerre-Polya classification of these theorem, which itself is not too hard to prove, but if you take that as a black box, then this is just a series of beautiful small observations, but then you make one observation after another, and they add up to this beautiful result through a beautiful proof. And again, in my sort of lecture notes or my book, I've tried to just now add both the sketch of that Laguerre-Polya result, a sketch really, and a much more detailed sketch of this theorem, and as well of the Schoenberg theorems, the Schoenberg classification theorems. And as I said, they're just a series of simple but extremely clever observations by all these old masters, and yeah, they add up to these amazing results. So now by Schoenberg's results that I just told you, you can add a third condition equivalently, which is 1 over psi gamma, 1 over the generating function, is a Laplace transform of a Polya frequency function, which is one-sided or two-sided. Okay? So one-sided is for the first kind and a general Polya frequency function for the second kind. Of course, assuming that it doesn't vanish at 0. So that under that minor assumption. Okay, so and then the final, I guess in the final slide, then I will end, as I said, I'm ending with some modern mathematics. So this is still very classical. And then people were trying to still understand. Can you classify them? Can we understand all operators? All these diagonal operators are understood. But what about non-diagonal operators, which still linear transformations of polynomial spaces, which preserve real rootedness, or which linear transformations of polynomials of degree at most n, which preserve real rootedness, or polynomials with roots in a sector or in a circle and so on, which preserve real rootedness. And somehow for almost 100 years, this was not known. In fact, as late as 2004, there is this survey by Craven and Chordas, if I'm pronouncing his name correctly, which says that the maps preserving preserving rootedness in, say, a sector centered at 0 or on the real line, the real rootedness, things were not known. The multiplier sequence, the diagonal matrices were known. The non-diagonals were not known. And then somehow in the late 2000s and in the early 2010s, Julius Borchia and Peter Brandon showed all these amazing results, went back to this classical program of Laguerre-Polya, Schur, and so on. And I'm just mentioning a few things here that they did. They provided higher dimensional versions of Polya-Schur multipliers. They also provided classified linear operators on polynomials of one and several variables that preserve these properties, these root location or root preservation properties. They allowed, similarly for stability, they proved three conjectures, I think, of Charlie Johnson, Lee-Yang type theorems, a bunch of things. And then one more notable paper on negative dependence and strongly Rayleigh measures. So with Tom Liggett, who was, I think, also a student of Carlin at Stanford, they developed this theory of negative dependence, and that enabled them to prove conjectures of all these people. And this circle of ideas, in turn, was taken along with, I think, something called apolarity. I am not an expert, again, in this part, by Adam Marcus, Dan Spielman, Nikhil Srivastava, in this decade, or just the decade just gone by, to prove all these famous results that, again, people know of. And so, but really, all of this stems from this extremely classical program of understanding, polynomials and zeros of them, understanding the limits of such polynomials, the Laguerre-Polya class, and then the two parallel offshoots, well, not parallel, the two offshoots. One is the Polya-Schur multipliers, and one is Schoenberg's results on Polya frequency functions. And and this is still active and very, very much so even today. So it's a wonderful classical area which still is evergreen in modern mathematics. Okay, so just for some references, so the notes that I was mentioning, as I said, they're on my website. They are still being updated. So I'm giving a talk in 2 weeks' time, and I hope to have a much more complete. I mean, it's almost done. I'm just putting in a few more results on Hermite Beeler and Gauss-Lucas and Ruth Hurwitz and so on. But more or less, the Laguerre-Polya, Schur, Schoenberg part is already updated in there. And then here are the historical papers. Laguerre 1882, Polya 1913. These were the Laguerre-Polya class functions papers. Polya and Schur classified the multipliers, the diagonal multipliers in Krell in 1914. Gantmacher and Krein had this famous the spectral properties of totally positive matrices, not kernels here. And Schoenberg introduced Polya frequency functions in 1941. So yeah, that's it. Thank you.
Okay, so very nice talk, Apoorva. Maybe now, if you don't share, if you press escape, it might, yeah.
Sure. Yeah.
Then we can probably see you and other people. So, any questions?
Yes.
Well, a couple of small questions, Apoorva.
Yeah.
Go ahead.
Can I ask?
These not. I mean, if you take the non-diagonal multiplier as given by a polynomial product, point-wise product of two polynomials. So yeah, do we know anything about such multipliers?
Yeah, I think they know. So I kept a printout here in case I get that some kind of such questions. But yeah, so Borchia and Brandon actually classified these kind of maps, and I mentioned that here. Basically, there's something called the symbol of an operator. So the idea is maybe the following: you take x plus. So the classification of Polya-Schur multipliers itself is the following. A sequence is a Polya-Schur multiplier if when you act on x plus 1 to the n, just x plus 1 for all n, then the polynomial stays real. So now you basically mean summation n choose k, gamma k, x to the k is real root. And that should be true for all n.
Okay.
Yeah. So
Who
that
has
is.
proved this?
I'm sorry?
Who has proved this result?
This is Polya and Schur's original one. So you just multiply the gamma k to x plus 1 to the n. Now, instead, for all linear operators, what you can do is you can look at the following. You look at x plus y to the n, and you operate. So suppose I have a linear operator t. Okay, I look at t of. So instead of multiplying by gamma k, I look at t of x power k. Right. So in the multiplier sequence, t of x power k was just gamma k times x power k. right? And so T of x power k, if you replace that there instead of so then instead of x plus 1 to the n, you look at x plus y to the n. And you claim that this polynomial is now a polynomial of two variables. So summation n to k, x to the k, y to the n minus k. Replace x to the k by the action of that operator t. So you get summation n choose k, t of x power k times y to the n minus k. That polynomial must be stable. Stable means it should have no root xy with both of these imaginary components of positive. So it's a characterization in this intrinsic sense. I'm not sure if, but maybe one has to look at Gautier and Brandon's paper to understand if you specialize to t of xy, t being a multiplication by some specific polynomial, then is it true that you can classify those polynomials themselves? I'm not sure myself, yeah, but you may have to check the paper itself. But the general operators have been classified in that sense, that the symbol is stable. I mean, t of summation n choose k, t of x to the k times y to the n minus k is stable for every x and for every n.
Okay. And secondly, these Polya frequency functions, has anybody considered their infinite dimensional analog? I mean, like in the Hilbert space setting or Banach spaces?
I don't know. If one has to check. I don't know. This is
So like,
so in what sense do you mean on Banach spaces?
So for example, for positive definite functions, we have a very rich theory in the Banach space setting. I mean, which leads to isometric embeddings of Banach space into Hilbert space using
positive theory. Yes, of course, exactly.
Right. But then I don't know whether the Polya frequency functions have been studied in that setting.
Yeah, I mean, but again, I think so this was about distance matrices embedding into Hilbert spaces or Banach spaces, right?
Mm-hmm.
Distance means, I mean, metric spaces embedding into Hilbert spaces or Banach.
Hilbert space, right.
Right. So, yeah, so I'm not sure how metric space that kind of a connection would embed into Polya frequency. So, yeah, I mean, no, I'm not sure. So,
Can I ask?
Yeah, sure, go ahead.
Yeah, to continue with this multiplier sequence, Allaway and Zafranic took the multiplier sequence applied to any system of orthogonal polynomial systems. And Frank Filbier, Girgenzon, Ritit Zwark, my student Anu Saxena, and I have a paper on simultaneous preservation of orthogonality. That means you take one orthogonal polynomial system, take the multiplier sequence the way you did to monomial, then does it preserve orthogonality of another polynomial system or not? And we gave characterization and studied further properties. That is in computational analysis in 2000 plus minus. And then my student Anu Saxena, her PhD thesis is on this only. We call them dilation operators. And then coming from different orthogonal polynomial systems, then we study the differential operator corresponding to the effect on other orthogonal polynomial system. And then the spectral theory. And the spectrum changes from small sets to full plane. Because the basis changes. So the unboundedness enters in, even though the original multiplier sequence could be bounded coming from one orthogonal polynomial system. So your multiplier sequence, which even Brandon and Borsia study, I was in touch with them regarding this multiplier sequence also. But I didn't know the characterization that you gave today. So I got very much interested in terms of Laguerre-Polya class. Anu Saxena has put up her paper on archive, recent one for further work. And her thesis is old, 2004-5. But her paper is, 3 years ago or something. That is one thing coming from multiplier sequence, last thing first, sort of, Next is, I heard a lecture on Laguerre-Polya class in one of the webinars. So I will dish that out and send my correspondence with the speaker to you. Okay?
Sure, that sounds good.
And total positivity, of course, I'm always interested. Thank you for the wonderful talk.
Yeah, so it's really wonderful talk. Any other questions, comments?
I just wanted to make a comment. Sophie asked, no? So this Bhatia's work about one parameter convolution semigroups of symmetric measures, continuation, that would give you an infinite dimensional symmetric matrix as convolution operator, right? And then there are things he has done where you can take power alpha, which is still symmetric because of these the one parameter semigroup. Sophie might be interested in that.
Right. So is it given in his matrix analysis?
I don't remember. I heard a talk by him a couple of times where he had that. One was in Delhi University, another was in RMS meeting. So, but it must be somewhere. I can find and send you.
Maybe Tanvi would know. Tanvi, do you know the reference or the year?
Me?
Yeah,
Tanvi. Is Tanvi there?
She's there, I think. Anyway, so.
Hello, Arvita.
Okay, any other questions, comments? Okay, so let us yeah, sorry.
I mean, I will have to catch up with Apoorva's first part sometime when we meet, because I missed it out yesterday as well, the same talk. Yeah, I missed the first part. Yeah, same thing happened today. So I hope to meet you, courtesy COVID, sometime soon.
It is recorded, so you can ask Gaurav for a
That's right.
link.
I can send you a link to the recording.
All right.
Catch up the first part.
Will it be available on the YouTube of some time?
I don't know about YouTube, but I'll send you a link. Somehow you will be able to see it.
Please do. That would be great. Thank you. Thank you, Gaurav.
Yeah.
Sophie, you are in Kashmir still?
Yes, in the double whammy. Right. I'm in Kashmir. I have not been able to move out all these months like everybody else, of course.
Yeah, I suppose. We are all now in Kashmir. Not quite, but yeah.
Yeah, approximately.
I read about in the newspaper or some article I read somewhere about an app which enhances the speed even over 2G. Do you know about this?
I did try, but they didn't work. I heard something of that sort, but the other day I had to put up this Geo Fiber, and that's great. I mean, I'm able to watch nicely and correctly.
Was the slides blurred today? I think a couple of people said the slides were blurred. Was it so for everybody? Local connectivity issues?
No, for us it was very.
No, actually, today for a change, I didn't have any connectivity issues because I have 5G, which most of you won't have it.
Yeah, no, your video is coming very clearly, so I think you're on a good connection.
Yeah, slides
right.
Clear, so maybe some people who had problem with connection.
Because on their end, you think that may have been the problem. I don't know.
Clear slides.
For sure at their end.
Okay.
In fact, slides are unlikely to be blurred. It is the video that can be blurred.
Riddhi, why did you open your video?
Because Debashish is holding the computer.
He's speaking, I can hear him.
Yeah.
Oh, there you go.
We haven't put on the lights and it's getting dark slowly.
Yeah.
And I have this trendy haircut from the lockdown period. Self-inflicted. So
it's a good haircut, I think.
Yeah.
I think Apoorva has the same haircut. Is it self-inflicted?
This is from courtesy my wife. It's very good.
Mine is at least 3 orders of magnitude shorter.
I see.
I shot her randomly. So.
And I don't have to bother anybody for my haircut.
No, it's a good idea.
Another thing, you brought in Riemann zeta function also. And
Polya brought it.
And the Riemann zeta function is used in Brownian motion also. And there is a nice survey article 9912170. And Atul and you might like to look at that. And if you are interested, then we can request somebody to give an exposure to that, because Atul gave a very nice talk. Then another colleague of yours gave a very good talk. And now you are also mentioning that. So we can ask somebody to expose that paper, 9912170. It is Riemann zeta function and Brownian motion.
I see.
Oh, okay.
So
It's also cropping up everywhere else. It is in string theory, quantum field theory, and all
Yes.
that. Everywhere.
Yes,
It's a very important function. Yes.
right.
So, ma'am, maybe that is a good topic for you.
Pardon?
Someone could be you.
Robin Hudson and Alex Belton. So they may be interested.
Alex is chair of his department. I don't know.
Yeah, so we can ask him if you are interested. First, you have a look at it. Okay, it is a survey article some time ago. Okay, and then we can see.
Okay, that's a good suggestion. Thank you.
Okay, and if you are interested, then I can request him to give something about that, or we can request the authors only. Okay. But if you are interested, only then, because it requires a lot of background, of course.
So, Apoorva, you mentioned about this result. If the Riemann psi function is in Laguerre-Polya class,
that is your and
yeah. So, what I wanted to say was, I mean, recently Terence Tao and Brad Rogers have their result that the
De Bruijn constant, right?
Newman constant is greater than or equal to 0. And so Newman must also have had contributions in this area, right? The one where you were.
Sure, I think because papers I saw in the literature, but I didn't actually dig into.
Okay. So, the thing rests with proving that it is equal to 0 exactly. I don't know. Yeah.
Yes. Yeah.
Riti, are you hearing me?
I am hearing you. Tell what.
Can we continue after the talk is over after for 5 minutes? I mean, we can continue. I think that's possible, right?
Yeah, well, Gaurav.
No, even if they sign off, I think we can still.
I can call you on phone, no? WhatsApp. You have WhatsApp? Or
yeah, I do. No, I thought.